Hi everybody. First of all, I'd like to thank Thermo for inviting me to talk to you today about one of my favourite subjects, which is synthetic cannabinoids. Over the next 20 minutes or so, I'm going to talk to you a little bit about synthetic cannabinoid receptor agonists, give you some of the background to those, describe the analysis workflow that we've set up here at LGC, and then look at some new compounds that we've been detecting and some of the products containing those new compounds. So, synthetic cannabinoid receptor agonists, a brief history. In the mid-2000s, there were rumours of herbal smoking mixtures being sold online as legal highs that could produce strong cannabis-like effects. And these were things that were called spice, as you can see some pictures of them at the bottom of the screen. In 2008, the German and Austrian authorities actually investigated some of these products and identified something that was called JWH-018 in one of these products. In 2009, we at LGC were contacted by a long-standing friend of our lab, a guy called John Ramsey, who was heading up a company called Tic Tac Communications, who were involved with identifying pills and so on and so forth through a graphical recognition system. And he brought some spice gold and some spice diamond, two herbal incense products, and would like he said he'd like to run them on our new Orbitrap systems to see what we could find. In the analysis, we actually identified JWH-018 and something called CP47, which is what the Austrians and the Germans had found a few months earlier. Generically, these things are called synthetic cannabinoid receptor agonists, or SCRAs, and I'll be referring to these as SCRAs through the rest of the talk. So the Spice Diamond product that we tested in 2009 gave this very large peak here at about 5 minutes on our LCMS run, and it actually had an elemental composition of C24H23NO, which was consistent with JWH-018 that had been reported at the end of 2008. This is the MS2 spectrum that we generated, and you'll see that this is very similar to the data that was produced by the Austrians and the Germans on this particular compound. And the only difference, of course, being that we're using accurate mass as opposed to nominal mass. So what is JWH-018? It was first synthesized in 1995 by John W. Huffman's group in Clemson University in the USA to study drug structure cell receptor relationships, i.e. looking at how drugs interacted with drug receptors. It's never been tested formally in humans as a normal drug substance would be, and it's apparently 5 times more potent than THC, and that's backed up by some of the receptor-based assays that have been developed more recently to test for these types of things. Structurally, it's very dissimilar to THC, which is the main active ingredient in cannabis. It's now illegal in many. This slide shows a brief history of synthetic cannabinoids in the UK. CP47 was around very early on, JWH-018 at the same time. But then over the last 13 years or so, the main synthetic cannabinoids have basically maintained the same kind of structure. We've got a core of either an indole or an indazole moiety, and there are usually alkyl side chains which are either fluorinated or non-fluorinated. Sometimes there's a cyclic group on the side chain. The functional groups in the other position on the molecule, adamantile groups. You've got an amino acid on here, and lots of amino acid type derivatives on this particular part of the molecule. So where have they come from? First of all, JWH-018 actually came from some of Huffman's work in the scientific literature. Various compounds over the years have been worked on as alternatives to cannabis as treatment for pain, and obviously patents have been filed for those, and they are public access documents, so people have been pulling these things out. And more recently, there have been some truly designer synthetic cannabinoids produced in an attempt to evade legislation, as most legislation, at least up till recently, has been based on defined structures of compounds. So it only takes a slight modification to make the compounds legal again until the legislation catches up. And Huffman actually published a paper where he's talking about hijacking of basic research, i.e., people using his research to generate these particularly nasty compounds. So, what are the effects of SCRAs on the human? The effects are believed to be mediated through CB1 and CB2 receptors. These receptors, cell receptors, actually affect multiple systems in the human body, including the central nervous system, respiratory, cardiovascular, and immune systems. SCRAs are actually total agonists for these receptors. THC is a partial agonist, and if you remember, THC is the active ingredient in cannabis. So SCRAs and metabolites tend to have stronger affinities for receptors than THC, and this leads to greater potency and longer duration of effects. SCRA-related deaths are actually from the acute toxicity, stroke, heart attack, and suicide. There is more information around cause of death from synthetic cannabinoids now than there used to be, and if we look down the list here, these things seem to have a major effect on many systems within the body. So over the period of 2008 to 2019, looking across Europe, these are figures presented by the European Monitoring Centre for Drugs and Drug Addiction. You'll see that in 2008 we just had a handful of synthetic cannabinoids, but they grew to a peak around 2012 and 2013, where we were seeing probably 30 or more different compounds each year, and these have tailed off to really sort of less than 10 a year as we head towards 2020. But we find more of the individual finds. It's not suggesting that the total number of synthetic cannabinoids have dropped. It's just that the variation has reduced. And if you look at this data here, this is from our lab, and these are the findings that we've identified over the last 6 or 7 years. And all of these findings represent our major SCRA findings as a percentage of the quarterly totals detected. So if you look here, this was actually a compound called 5-fluoro-AKB48, and that was really nearly 100% of our findings in sort of 2013, 2014. And you'll see the duration of these things on the market is usually around 18 to 24 months, and there are probably 2 or 3 main ones at any point in time. The most common one at the moment is something called MDMB-4 in Panaca, which is making up probably about 65% of our findings. But there are these newer compounds coming online here called 4-fluoro-MDMB-BICA, 4-fluoro-A-butinaca, and ADB-butinaca that are starting to lift off, and they may well replace over the next year or so MDMB-4 in Panaca as the most prevalent in the UK. So how do we actually test for synthetic cannabinoids? We have a variety of extraction methods for each type of matrix that we're trying to extract synthetic cannabinoids from. So once we've prepared a sample, we analyze the sample down exactly the same methodology on a Q-exactive. We have an LC method which is based on an acetic acid methanol gradient, and it's quite a fast runtime. We're looking at a 5.5 minute acquisition time. It's in positive electrospray, and the workflow itself on there, the acquisition workflow, consists of full scan and full scan all-ion fragmentation. And we search this data against an accurate mass database containing over 1,000 SCRAs. And we also run a data-dependent MS2 workflow within the method. And this is initiated from an inclusion list that is generated from our accurate mass database, and we use a tolerance of plus or minus 2 millidaltons to fire off the MS2 scans. And our data processing is on TraceFinder. In order to describe the workflow in more detail, I'm going to present data on MDMB4 in Panaca, which is currently a significant problem in many parts of the world. On the slide, you'll see reports from both the European Monitoring Centre for Drugs and Drug Addiction and the World Health Organization. And this highlights really the global importance of this particular drug. So the first two elements of the analytical workflow on the QX Active are full scan and all-ion fragmentation, AIF. The full scan element runs scanning from 200 to 500 Daltons, and the AIF is from 80 to 500. And as you see here, this is an extracted ion chromatogram for MDMB4 in Panaca with a nice peak here. And this is the all-ion fragmentation extracted ion chromatogram for the major fragment ion for MDMB4 in Panaca. And this second peak here is actually a metabolite which fragments in the same way and gives the same major fragment ion. So all of our targeted compound data is held in an accurate mass data processing database, and you can see here all the entries for MDMB4 in Panaca. All you do basically is put in the molecular formula, and it will calculate the extracted mass based on the adduct and the polarity you're using. And here we have the retention time, and there are various other parameters around area thresholds for data processing purposes. You can export the information from the accurate mass database to an inclusion list, and our inclusion list has got over 1,000 analytes. This is generated directly from the accurate mass database, and here you see the information in the inclusion list. So there are about 1,000 lines in here, and this is the accurate mass of MDMB4 in Panaca, and this is what the instrument will use when it's doing data-dependent MS2. So moving on to the type of data that we see for data-dependent MS2, all these lines are MS2 events that have been initiated through the use of the inclusion list, and the data has been recorded in the data file. And this peak at 4.35 has a scan associated with it, and this is a fairly good mass spectrum of MDMB4 in Panaca. We can visualize the data that's been acquired for a single sample using TraceFinder. The peak in the bottom left-hand corner is the extracted ion chromatogram for the full scan element of the sample, and this is the correct peak for MDMB4 in Panaca. This is the fragment ion again, generated from the data-dependent MSMS. And this is a match of against the library that we've created in-house. This is a spectrum from the library. This is a spectrum from the sample. And as you can see, there's a very, very good match for MDMB4 in Panaca. So blowing that up again, you'll see there is a very good match here. If you look at the accuracy of the masses here and the relative abundances, we actually use an energy spread, as that gives a very good high and low mass spectrum. And it tends to be more information rich than just a single energy used for fragmentation purposes. As I said earlier, we're currently seeing a lot of MDMB4 in Panaca, but we've also started to detect this compound here called 4-fluoro-A-butanaca, and it's actually a 4-fluoro version of 5-fluoro-AKB48, which is, if you recall, the synthetic cannabinoid that was most prevalent about sort of 2014-15 time. ADB butynaca is a butyl synthetic cannabinoid, very similar to in that respect to the 4-fluoro-butynaca. And 4-fluoro-MDMB bica is a 4-fluoro version of 5-fluoro-MDMB pica, which was another major synthetic cannabinoid for us in about 2018. So these are all modifications of previous drug compounds. So this is a urine sample that tested positive for 4-fluoro-A-butynaca, and as you can see, through the use of extracted ion chromatograms for potential metabolites, we've identified a whole range of compounds. Most of these are hydroxylated in various positions. There's a butanoic acid metabolite, and actually there's the most common generally metabolite in fluoroalkyl compounds is this desfluorohydroxy compound. So if you look at the metabolite, here we're starting with the parent compound, and we're seeing replacement of the fluorine with a hydroxy group. We're seeing hydroxylation in the adamantyl moiety, and we're seeing combinations of these things as well. And there's also a metabolite through hydroxylation here and hydroxylation on the adamantyl. So these are mass spectra for metabolites of 4-fluoro-butynaca in the indazole fluorobutyl moiety. As you can see, the predominant ion in all these mass spectra is the adamantyl fragment, which is a 135 ion, and it's very hard to tell them apart other than the precursor ion. Likewise, metabolism in the adamantyl moiety, you're seeing a change from the 135 to the 151. And the dihydroxy is actually seeing that 151 going to the 167 here. Once again, because we're using the energy spread, we're actually seeing some parent ion as well, which helps in identification. So the other compound that I mentioned earlier as a newish compound is ADB butynaca. This isn't as widely metabolized, and the main metabolite here is this is basically it's an oxidative deamination product. We also see hydroxylations in both the indazole ring and the butyl side chain. ADB butynaca is another one of the new compounds that we're seeing. Parent compound, you can see, gives a major ion at 201. Oxidative deamination actually really doesn't change a great deal here, other than the precursor ion obviously changes. Hydroxylation on the indazole moiety gives a shift from 201 to 217, and actually hydroxy on the butyl moiety. That means that the 161 that you see on the indazole hydroxylation, it remains as 145 because the hydroxylation is occurring on the butyl. So hot off the press, so to speak. This is something that's been going on quite a lot in the USA. Gummies are basically sweets. Gummy bears is where it originates from. They've been found to contain CBD, which is a product coming from marijuana. And more recently, they've been found to contain synthetic cannabinoid receptor agonists. This is a sample that we got in the UK from a forensic seizure, and we tested it through our system. So when we looked at the data from the gummy extraction, we could see that there was a peak, largest peak here at 4.15, and the AIF data showed a very large ion of 232.1127, which is indicative of a range of synthetic cannabinoids. The elemental composition was confirmed here. We went and then did targeted MS2 to generate a decent MS2 spectrum, and once again we matched up with the AIF data with a 232 ion. The mass spectrum from the sample was similar to 5-fluoro-MDMB pica, but the precursor mass was a methyl group bigger. This suggested that the likely compound was actually 5-fluoro-EDMB pica. This was confirmed using NMR. And this really is hot off the press. This is a report from our recent bank holiday weekend where children have been taken to hospital after eating sweets, and it seems as though they contain cannabis. I wonder if these actually contain synthetic cannabinoid receptor agonists, as this seems to be fairly consistent with what we were seeing in our forensic sample. So in summary, we've seen that SCRAs keep evolving. We have got robust, high-resolution, accurate mass workflows that enable us to keep up with new compounds. New compounds are currently emerging that will replace MGMB4 in Panaca over the next few months, and this seems to be a cycle of about 18 to 24 months when a new compound will stay around. And we have actually just seen new ways of consuming SCRAs that have got major dangers for children, especially at this particular moment.